As we have seen in the previous video, achieving domain consistency for some constraint is very hard. It's NP hard. So we need to relax the consistency that we want to achieve for this constraint. And the relaxed consistency that we usually use for some constraint is bound consistency. This is the algorithm that I will explain in a few minutes. So the intuition first. So assume that we have here a sum of 3 variables that need to sum to 0. The domains of the variables are represented here. What I propose that we do now is that we filter the domain of x3. So for filtering, of x1. So for filtering the domain of x1, I will put x1 on the right hand side of the equality. And of course, I have a minus sign now that comes in this expression. Therefore, I will put a minus on the domain as well. So the minus 110 will become minus 10, 100. Okay, so that's the range of possible values for minus x1, not x1. Okay, on the left hand side, I have 2 intervals. So if I do the sum over the 2 intervals, I sum the minimums and I sum the maximums. What I get is 2466. These 2 intervals need to be equal. Okay, that's imposed by the sum constraint. So as you can see, this interval is completely included in that interval. So if you want to make them equal without removing any values, we need to update the minimum of that one and the maximum of that one, okay, because we need to take the intersection of the common values there. And so the one here on the right hand side will become minus 66 minus 24. 2466. But because, if you remember, that's the interval for minus x1. So if we transform the interval to come back to the interval for x1, the domain of x1 will become minus 6624. That's exactly the kind of reasoning that we will do for achieving bound consistency for the sum constraint. Okay. Let's write down the equations now. First, the feasibility check. As you know, when we introduce a new variable, we need to verify that it's consistent, at least consistent. We will consider that the sum constraint is consistent if, by summing the minimum of all the variables there and the maximum of the domains of all the variables there, so we sum all the maximum values in the domains there. This is what I use as notation, xj min for the minimum of the domain of xj, and xj max for the maximum of the domains of xj. Okay, the sum of these n variables must be equal to 0. Therefore, if 0 belongs to this interval, then we will say that the constraint is feasible. Don't forget that it's a relaxation because we are only reasoning on the bounds of the domains there. Then for the filtering, it's pretty similar to what we did before. So for updating the minimum of the variable xi, I will do the sum over all the other variables, but I will take the opposite of the maximum of their domains. And for updating the maximum, I will sum over all the other variables, but I will take there the sum of the opposite of the minimum of their domains. Okay? And coming back to our example, this is exactly what we did. Okay? So to update here the minimum of x1, which was minus 66, you can see that we took the opposite of the maximum of the domains of the other 2 variables. So the opposite of 6 plus 66, okay, minus 66, that's the new minimum for x1. Okay, so the time complexity to filter one variable, if I compute the sum there from scratch, will be order of n. But then if I need to sum the domains of all the variables, this will require at least order of n squared to do bound consistency for the domains of all the variables involved in my sum constraint. So that's pretty costly. Let's see how to lower a little bit this time complexity. The idea is that we will pre-compute the sum of the minimums and the sum of the maximum of the domains of all the variables that appear in my sum constraint. So I pre-compute here in a variable an integer value there, s min and s max. I will pre-compute the sum of the minimum of the domains and the sum of the maximum of the domains. Once these 2 values have been computed, it's quite easy to check the feasibility in constant time. I just verify that 0 is between smin and smax. And for the filtering, once these two values have been computed, filtering one variable can also be done in constant time. Because if you remember, we needed to sum over the minimum and the maximum of all the other variables, okay? And so to filter xi min, I take the opposite of s max, but I need to cancel the contribution of xi max in this value. And so I sum xi max there because I took the opposite there. So by doing that, I cancel the contribution of xi max in this sum, and that corresponds to the new minimum for my variable xi. And that's exactly the same type of reasoning for updating xi max. I cancel the contribution of xi min in smin by summing back this value, okay? So you know that inside this one, I've got somewhere minus xi min. And so these two values will simply be cancelled. And so what I get there is the sum over all the variables j different from I, okay, as j min. And so if I can do that in constant time for one variable once smin and smax are available, doing it for all the variables is now order of n. And so I have lowered my complexity, my time complexity from n squared to order of n for filtering the sum constraint. We can improve again further this algorithm by making it incremental with respect to the search tree traversal. Okay, because the idea is that when we will go down in the search tree, which is represented there, sometimes the decision that we will take or the fixed point computation will lead to fixing some variables appearing in my sum to some values. Okay, some variables will become fixed. And the goal there will be to keep track of the sum of the fixed variables, and I also need to keep track of which variables are not yet fixed. Okay, because that's the one that have chances to be filtered. Okay, so to do that incrementally, I will use two state integers, okay, for maintaining the sum and the number of fixed variables. Okay, and we will use again the sparse set IDs that we have already introduced for implementing the domains of the variables to keep track of the set of unfixed variables. So we will keep a clear separation between the fixed indices of fixed variables, indices of not fixed variables. The goal there is, of course, that all these states of the partial sum and of the fixed variables and the two sets is automatically recovered on backtrack. Okay, this is why we use state integers, so stateful integers instead of simple integers of Java. So let's see what happens there. Sum fixed is the sum of the minimum of the fixed variables. So I could take the maximum, that would be the same because these variables are fixed. And so the smin will simply be the sum of the fixed ones plus the sum over the ones that are not fixed there. And for the sum of the max, that's exactly the same value that we have there because they are fixed, plus the sum over the variables that are not fixed of the maximum of their domains. And you can already see that the benefit of doing that is that the sum there is less expensive to compute. If there are only a few variables that are not fixed, it's less expensive than doing it over all the n variables. So initially in my search tree, the set of fixed variables is empty and the sum of the fixed is 0. Then if I take one decision of fixing one variable, x0 is equal to 4, the sum of the fixed becomes 4, and the set of fixed variable is now including the index is now including the index of the variable x0, which is the one that I just fixed. This decision removed the value 2 from x5, so it's not a decision of fixing one variable. Nothing changes for the state of my sum constraint. Then I fix one more variable, so x5 becomes fixed to 1. Therefore, I need to add 5 to the index set of the fixed variable, and the sum of the fixed values there will now become 5, because you have one plus 4. This is the total contribution of the fixed variable in the sum, which is equal to 5. Okay. One more is fixed. So now I also need to add the index 2 to this set of fixed variables, and the sum of fixed, I do a plus 6 because of that one, and now the sum of the fixed ones is equal to 11. Okay, but a sparse set would be nice to keep track of the set of unfixed variables, but it's only able to shrink. So instead of maintaining the fixed one, I will keep the complement set, which will be the unfixed variables. So the unfixed variables contain all the variables at the beginning. Once you see that one of them becomes fixed, I simply remove the corresponding index. So x here, index 0 has been removed. Okay, but that's pretty similar. Okay, it's exactly the same as before. Okay, how do we maintain these sparse sets now? I will depict the state of the sparse set there. So again, what I have here is a sparse set, and I will use a separation which is represented in red. That will clearly split the indices on the left of the fixed variables and on the right the ones that are not yet fixed. Okay, so the sum of the fixed is 0 and the number of fixed is 0, and this is why you see that the red bar is completely put on the left initially. That's the code that will update my sparse set. Okay, so when x0 becomes fixed to 4, I have here a loop that will loop starting from the number of fixed ones up to n, the number of variables, and it will make the corresponding update of the sparse set there that I will explain just now. So this one is fixed, okay? But you start on this index, so the only thing that you need to do to update the separation is increase the number of fixed here by 1. And so this is what you will get. The separation is there. You see that on the left, we have the variables that are fixed, and there is only 0 at that stage. And of course, I update the state integer that maintain the sum of the fixed variables. So 4. Then this decision has no impact, but this one will fix one variable. So x5 is equal to 1. I will loop over all the variables. This one is not fixed, not fixed, not fixed. But here something happens because we detect that at index 5, the variable is fixed. What we will do is that we will do an exchange with the variable in the first position and the current position, because 5 now should be included in the set of fixed variables. So we will make a swap of the two indices. We can do that in constant time. And then we simply increment the number of fixed variables to make sure that this one will now be considered in the set of fixed variables, but that will be fine. So we do this, we realize that it's fixed, we do the exchange, we do the swap, we increase the number of fixed by 1, and now 5 is part of the set of fixed variables. And of course, I also update here my sum of fixed, which is now 4 plus 1, and it will become 5. One more variable is fixed. Again, I execute my loop there over the not fixed variable. I realize that I'm progressing with my value I. I realize that it's fixed. I do the swap. I increase the number of fixed by 1, and now the index of variable 4 is considered as part of the set of fixed variables. Okay, so that's for the incremental update of the set of fixed or not fixed variables. We do a partition of the two using the sparse set trick, and we also keep track of the sum of the minimum of the variables, of the fixed variables. And on backtrack, this is the main benefit of this data structure, of this implementation, is that by only reverting two integers, all the states will be restored and we will recover the unfixed variable in our set. Look, assume that we backtrack by 2 levels there. So x5 and x4 should be back in the set of not fixed variables. And this is exactly what will happen. We just need to decrease the size by 2 there, and they will be back in the set. Okay, like this. Okay, and this is automatically done by using the method on the state manager. We just do a restore state 2 times, but this will be done by the state manager, by the search. And so all the variables are back in the set of not fixed variables. And of course, that's the same for this partial sum. In the next video, I will discuss about the fixed point of the sum constraint. Okay, that's something that we need to pay a little bit attention to.